Math 2414, Surface Area of Revolution, Video 7, Surface Area Example 5. Before we begin this last video, and this is specifically for my students, in case somebody else is watching this, I can't cover every possible scenario that's going to happen in these integrals. If you've done the homework over arc length, you know that how bad the integral is depends upon the function and what it does or does not do. So as you venture into your homework, expect to see some issues that are not exactly like what you saw in these videos, but you've encountered previously from arc length problems. All right, so here's the problem. Find the lateral surface area of the solid obtained by revolving the graph of f of x equals y equals x cubed. So that's left over from the previous video. Originally, it just said y equals x cubed over the same interval, x is from 0 to 2, around the y-axis. So what's the difference? And if you're like, what do you mean? In the previous video, we did this exact same problem, except there was one difference. If you spotted it, it's the axis of rotation. We're rotating around the y-axis. So now we're taking this thing and we're not doing this to it, we're doing this to it. Which will give us kind of this bowl shape. The other one was more like a top, or a circus tent if you look at it from the right perspective. But now if we rotate this, we'll just get a bowl, and we want to know what its surface area is. So how hard can it be just changing the axis of rotation? Well, speaking of the axis of rotation, since it's the y-axis, we're going to set up this integral. I'm going to move the picture because it's going to be in the way. All right. So our surface area, almost said surface integral, that is a totally different thing. Our surface area will be calculated using this version since we're going around the y-axis. 2 pi x ds. How do we unpackage the ds? Well, we have a function of x, so we want to unpackage it with a dx. So the integral of 2 pi x square root of 1 plus the square of the derivative of f dx. Well, we already know what the derivative of this, the square of the derivative is, even though I botched it up in the last problem and caught it in time. But I also want to point out that the variable representing the radius is the correct variable, so I don't have to replace it. And we're doing a dx integral, so it's going from 0 to 2. 2 pi x square root of 1 plus the derivative is 3x squared, and when you square that you get 9x to the 4th. And now we're here. How should we integrate this? I'll admit the trick to integrating this is not straightforward, but it's also not impossible to follow. It's just another example of practice, 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 or witness, witness, witness. First off, we can't do a direct substitution. Because if we did, the natural choice would be u equals 1 plus 9x to the 4th. But the problem with that is that when we take the derivative, we get 36x to the 3rd dx, and we don't have enough x's to build the du package. Constant multiples, those are easy to throw in and balance. Missing variables, no. I mean, it's not impossible, but in this case, trying to balance it, because we would have to throw in a couple of extra x's and balance it with an x squared on the bottom. But what are we going to replace this with? Well, we would have to solve this for x and then square it, and it would just get uglier. So just no. In general, you don't try to balance variables. It's not impossible, and maybe sometimes you should consider it and hope something nice happens. But I'm telling you right now, not going to happen. So bad substitution. So now what? Well, the reason I wanted to do this was for two purposes. Number one, to show you that simply changing the axis of rotation can drastically alter the calculus problem that you have to do. And number two, to kind of get you inside of my head to see some motivation on how to attack some integrals. When I was working this one out, and I'll be honest, when I set this up, I didn't know if it was going to be integrable. There are functions that are not possible to integrate. By the way, you can use techniques to approximate this, And for those of you familiar with Desmos.com, you can actually type this in here and it'll give you a decimal approximation. But in terms of actually calculating the antiderivative, I want to take this opportunity to get you inside my head to let you know how I cracked this one. Anytime I see 1 plus a power, I instantly think trig substitutions. Well, trig substitutions involve squares. This is not a square. I said, no, it's not, but it used to be. So I'm going to unsquare this just for a second. Take it back to 3x squared squared. If I said u equals this guy, I would have 1 plus u squared, and that looks like something that we could do a trig substitution to. Just remember that trig substitutions are usually for expressions of the form a squared minus u squared minus a squared, or a squared plus u squared. And with the correct trig substitution, you can take advantage of the Pythagorean identity to collapse these binomials down to single terms. So sometimes you have to smack the problem around just to get it ready for a trig substitution. I'm going to choose to let u equal 3x squared. The other thing that motivated the substitution is that if I took the derivative of this, I would get 6x dx, and I've got that for a du package. I don't have a 6 yet, but that's easy to fix. So we're going to let u equal 3x squared and reevaluate. Let's go ahead and change the limits of integration. X equals 2 implies that u is equal to 3 times 2 squared. 2 squared is 4, 4 times 3 is 12. And x equals to 0 implies that u is equal to 0. That should be pretty obvious. So let's balance out the du and then change this to, balance out the du package, then change this to a u integral. I need a 6 for my du package, so we'll put a 6 there, and I'll balance it with a 1/6. And now, let's change this integral. I'm going to move it over here. All right, first let's take care of the 2 pi. Let's move it outside here, put it with a 1/6. Make it a 2 pi over 6, which I'll reduce in the next line. I just wanted to see where the pieces go. The limits of integration change from 0 to 12. The x, all this double underlined stuff collectively becomes the du. So all that becomes the du. And then under the square root, I still have the 1, but the 3x squared becomes a u, and that had a square on it. So in other words, this is the u, so now I have 1 plus u squared. So I didn't really do the integral, I just changed it in something a little bit more familiar, because when I see a binomial, I instantly think, can I do a trig substitution? Well, let me make it look right before I consider it. All right, so now we're here, we'll call this pi over 3 in the next line. As a trig substitution, if you go back and review trig substitution, this is let u equal tangent of theta. Then du is equal to the derivative of tangent theta, which is secant squared theta, d theta. Now, I know this is a definite integral, and we could consider changing the limits of integration, but these are u values, and so to solve for theta, I would have to use tangent inverse. Tangent inverse of 0, I'm not worried about. Tangent inverse of 12, I'd rather not drag that along. So I'm going to leave the limits of integration as is, but because I'm going to change this to a theta integral, there's my pi over 3. And I'm going to leave the limits of integration as u. I'm going to explicitly state this is going from u equals 0 to u equals 12. All right, under the square root, I get 1 plus u squared, but u is tangent, so I get 1 plus tangent squared. Du becomes secant squared theta d theta. And let's see what this does. Pi over 3, integral, u equals 0, u equals 12. 1 plus tangent squared is secant squared. The square root of secant squared is secant, times the secant squared over here gives us secant cubed theta, d theta. Now, if we hadn't seen this integral before, then we would have to do some shenanigans. We would split off the secant squared, change it to 1 plus tangent squared. No. We would do an integration by parts, and then at some point the integral of secant cubed would show up again and then we would solve for it. But I like to file the integral of secant cubed under stuff that we've done already and previous results. So I'm not gonna recalculate the integral of secant cubed. I will, however, use its results. So, see, I'm running out of room here. Since this is the last video, I guess I can get rid of this. All right, so over here, I'm just gonna say recall that the integral of secant cubed theta, d theta, is 1/2 times the product of secant theta and tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. Kind of running into room over here, running into stuff over there. And again, that can be obtained by doing an integration by parts on secant cubed. You would split it back into secant squared times secant. You would let dv equal secant squared theta d theta, because that's easily integrable. And you would let u equal secant theta, which is easy to differentiate. Set up integration by parts, do a little bit of Pythagorean identity substitutions, and you expose another secant cubed integral, at which point you would solve for it and get this. But let's pretend that we have this at our disposal. Now we have pi over 3. Antiderivative of secant cubed is 1/2, don't need that in parentheses yet, 1/2 times secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. And this is being evaluated from u equals 0 to u equals 12. All right. So now we got to get the u's back. And remember, in a trig substitution, and I should have done it back here, there's always a picture associated with it. If you came up with an angle theta, I need its tangent to be u. Since tangent is opposite over adjacent, putting u for the opposite and 1 for the adjacent would give us the correct value of tangent. Using the Pythagorean theorem, we would get the square root of 1 plus u squared for the hypotenuse, which we may need over here. All right, so let's change these thetas back to u's using the triangle, and while we're at it, pi over 3 times 1/2 is pi over 6. All right, secant is a reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. The square root of 1 plus u squared over 1 is just the square root of 1 plus u squared. And tangent of theta, well, that was u. So let's put it in front of the square root, because putting things after square roots multiplicatively, bad idea. Let's write that a little bit better. U times the square root of 1 plus u squared. So that's tangent of theta, this is secant of theta. Plus the natural log of the absolute value of, well, secant of theta was the square root of 1 plus u squared, plus tangent of theta was u. Absolute value, close parentheses, being evaluated, and now that it's the correct variable, I can just write 0 to 12 and then plug away. All right, let's see how efficiently we can do this. If I put 12 here and squared, I get 144 plus 1 is 145. So we get 12 times the square root of 145 plus the natural log of, I can lose the absolute value now because 12 is going to keep this positive. It's not wrong to have the absolute value, it's just kind of redundant. Well, this is still going to be the square root of 145 plus 12 minus, now let's talk out what happens when we put in 0. Some of my students are still in the bad habit of just ignoring a 0. You can only ignore a 0 if it's a lower limit, not an upper limit, a lower limit, and it annihilates the antiderivative, meaning when I substituted, the antiderivative is 0. So let's talk it out. If I put a 0 here, it's going to be 0 times, and that kills that. If I put a 0 here, I'll get the square root of 1 plus 0, which is 1, but then take the natural log of 1, which is 0. So this 0 does annihilate the antiderivative, so it's gone, and I believe we have our answer. So what's the moral of the story? some of these problems suck. Not really. This one was actually manageable. In a second, I'll show you one that I set up that wasn't. The moral of the story is just changing the axis of rotation drastically changed the integral. Not the setup, but the evaluation. And I'll be honest, this move here, about letting u equal 3x squared to turn this into something that we could do a trig substitution on, is not an intuitive move. It comes from practice and experience, and now you've just experienced it. But anytime you see a binomial, you can always ask yourself, hey, can I make it look like something for a trig substitution? Speaking of problems that I didn't do, you see behind the scenes here. There's that guy. That's the previous video. I thought about doing this one from a dy. And so I'd set it up as a dy. I'm not going to go through all this, but it set up an integral that I could not see an easy way out of, so I wasn't going to waste your time with it. And there's the one that we just did. All right, so that was fun. And that's the end of this series of videos.